Hello students, welcome to the chapter Differentiability of the function. In this video, you are going to learn the definition of differentiability, left-hand derivative, right-hand derivative, and a very important theorem. So before that, let me recall the definition of derivative of the function. The derivative is defined as, let y is equal to f of x be a function, then derivative of y with respect to x is denoted by dy by dx and is defined as limit h tends to 0 f of x plus h minus f of x divided by h exists. That means whatever limit exists for f of x plus h minus f of x divided by h as h tends to 0, that is called as derivative of the given function. That means you have to operate this one, limit. So when you operate this, whatever the answer you will get, that answer is called as derivative of the function. So that is dy by dx is nothing but limit h tends to 0 of f of x plus h minus f of x divided by h. The derivative is also denoted by f dash of x. There are so many notations used for dy by dx. So remember students, one is f dash of x. Like this we have many notations, many different notations we use for dy by dx. So next is derivative of the function at x is equal to c point. So it is also very simple. In this definition, just replace x by c point. That become derivative of the function at c point. Okay, see here, y is equal to f of x be a function and c be any point. The derivative of y at point c is denoted by dy by dx, x equal to c, and is defined as limit as h tends to 0 f of c plus h minus f of c divided by h. That is dy by dx at x equal to c equal to limit h tends to 0 f of x plus c plus h minus f of c exist. See, dy by dx is also denoted by f dash of c, and this definition is rewritten as in this way: f dash of c is equal to limit as x tends to c f of x minus f of c divided by x minus c. So this is also called as definition of derivative at x equal to c. So this definition is equal to this only, because just in this definition c plus h is taken as x, c plus h term, this is replaced by x term. Now if you take this as a x, then denominator h become x minus c, therefore h is replaced by x minus c, and here h is tending to 0. Now we taken this as a x now, as h is tending to 0 point means x is tending to c point. So therefore both are equal only. This definition and this one both are same. I hope you understood this one. So next is left hand derivative. As we have for the limit, left hand limit and right hand limit of the function, in the same way we have left hand derivative and right hand derivative for the function. So first let me define left hand derivative. It is in short written as LHD. Next is definition. The left hand derivative of the function with respect to x is defined as limit as h tends to 0 bar f of x plus h minus f of x divided by h. exist, which is same as definition of derivative, but here the tending point h is approaching, that is this point h is approaching 0 bar, lesser than 0 to 0. So lesser than 0 to 0, when you operate this, that become left hand derivative. Now derivative at c point, it is the same, just x is replaced by c point. Okay, f dash of c bar c minus limit as h tends to 0 minus f of c plus h minus f of c divided by h. So next is right hand derivative. So now easily you can define a right hand derivative. Just in the definition of derivative, we change tending point 0 to 0 plus. Right hand derivative, in short, we write RHD. The right hand derivative of the function with respect to x defined as limit as h tends to 0 plus. So here you can see the changes. H tends to 0, here we are taking 0 plus. So plus denotes that the derivative whatever we are getting, or limit whatever we are getting, that is right hand derivative. F of x plus h minus f of x divided by h exists and is denoted by f dash of x plus. Next is right hand derivative at particular point. This is general x variable. Next is particular point. So as I said in previous definitions, the general variable x is replaced by c point. F dash of c plus is equal to limit as h tends to 0 plus f of c plus h minus f of c divided by h. So this is called right hand derivative. So in the up to here you learn that definitions of derivative at c, left hand derivative and right hand derivative of the function. So remember these definitions, these are very important. So next is differentiability. So a function is said to be differentiability. It's very simple, students. If derivative of the function exists, then it is called as a differentiability. That means whatever we have definition for derivative, if that exists, means for the given function itself is called as a differentiable. Okay, or so first let me define this first definition. A function y is equal to f of x is said to be differentiable if limit as h tends to 0 f of x plus h minus f of x divided by h exists. That means which is same as derivative. Or a function y is equal to f of x is said to be differentiable if left hand derivative and right hand derivative exist and it should be equal. So if left hand limit exists, right hand limit exists, but they are different, means derivative of the function does not exist. If both are exist and if it is equal, then function is called, then it is called a function is differentiable. Okay, that is limit as h tends to 0 minus f of x plus h minus f of x divided by h equal to limit as h tends to 0 plus f of x plus h minus f of x divided by h. Now differentiability at particular point. So it is very simple. As I said earlier, change the variable x to c point. A function y is equal to f of x is said to be differentiable at c if limit as h tends to 0 f of c plus h minus f of c divided by h exists, or a function y is equal to f of x is said to be differentiable at x equal to c if left hand derivative and right hand derivative at c exist and equal. That is, limit as h tends to 0 minus f of c plus h minus f of c divided by h equal to limit as h tends to 0 plus f of c plus h minus f of c divided by h. That is, this is left hand limit and this is right hand limit. Sorry, left hand derivative and this is right hand derivative. Both should be equal. Okay. Next is, remember the following points. Now you learned that the definitions of differentiability and left hand derivative, right hand derivative, general as well as particular point. Now the differentiability in the interval, given interval, closed interval. A function y is equal to f of x is said to be differentiable in the interval, in an interval, closed interval a comma b, if it is differentiable at every point of a comma b, open interval a comma b. So students, here you can see that it is open interval a comma b, and in the open interval meaning, you know that excluding a and b. Okay, so therefore you consider any point in between a and b, at that point it should be differentiable in between a and b. Now excluding a and b. Now at the end point, because it is a closed interval and a and b, so at the a point and b point, what should happen? A point right hand derivative at a point, it should be exist, and left hand derivative at b point, because before the b point we have to consider, before b point to b point. So therefore left hand right hand derivative at a, that is f dash of a plus, and left hand derivative at b, that is f dash of b minus. Here actually plus is not written, okay, here minus is not written, okay, so make this changes. Here it is a minus and this is b, sorry, this is a plus and this is b minus. It should be exist. So that is h tends to 0 plus f of a plus h minus f of a divided by h, and limit as h tends to 0 minus f of b plus h minus f of b divided by h exist. Between a to b, for all the number it should be continuous, and at end point right hand derivative of the first point and left hand derivative of the second point, it should be exist. Next point, a function f of x is said to be not differentiable. So far I discussed that for differentiability. What are the, for not differentiable, remember there are 3 points. One is limit does not exist for this operation, that is limit as h tends to 0 f of x plus h minus f of x divided by h, that does not exist. Or second point is left hand derivative, right hand derivative does not exist, any one does not exist. Third point, exist, left hand derivative and right hand derivative exist, but they are different, that is they are not equal. If any one of these condition satisfied, or if any one condition holds, means we say that function is not differentiable. Okay, so this is whatever I discussed, this is a theory part. Next is, we have one important theorem on the differentiability and continuity of the function, so that I am going to discuss. So theorem is, if a function f is differentiable at c point, so understand here students, f is differentiable at c point, then it is also continuous at that point. Okay, the statement is very simple. If the function is differentiable at any point, then it should be continuous function at that point. Okay, so let me prove this theorem first. Given that f is differentiable at c, so what we can write, we can use the definition of differentiability at c point. So here I am using the second definition, that is limit as x tends to c, f dash of c is written as limit as x tends to c, f of x minus f of c divided by x minus c. Whatever before I discussed in the derivative at c point, the second definition that I am taking. So next, c is, now for x is not equal to c, what we can write, for x is not equal to c, we can write f of x minus c, f of c in this way, f of x minus f of c divided by x minus c, x minus c. Here remember, this x minus c get cancelled and it becomes same as left side term, because we have to prove that it is a continuous function. To prove that, let me go for this step. Let me operate f of x minus f of c. Let me take this one, f of x minus f of c, and this f of x minus f of c rearranged like this, f of x minus f of c divided by x minus c divided by x multiplied by x minus c. So which become equal to same as f of x minus f of c, that is left side. Next, take limit for this as x tends to c. Take limit as x tends to c on both sides. Okay, taking limit as x tends to c, right side also for entire term, limit as x tends to c. So next, using the properties of limit, we can take the limit separate. Left side taking the limit for this function and taking the limit for this second term, and then in this right side also same, limit for the first part and limit for this second term x minus c. And next is limit as x tends to f of x remains as it is. This become as x tends to c, limit of f of c same as f of c, and here this become f dash of c, because definition here you can say that this is nothing but f dash of c. I denoting this as f dash of c, and into 0 point, because as x tends to c, c minus c become 0, so it implies right side becomes 0, and then minus f of c, if you transfer right side you get f of c. See, now what we got the equation last step, with the help of this f dash of c is equal to limit x tends to c, f of x minus c divided by x minus c. From this we got limit as x tends to c, f of x equal to f of c, which is nothing but continuity of the function at c point. Because if the function is continuous at c point, then limit should be exist as x tends to c point, and f of c point should be both are equal. We got the same case. So therefore, if any function is differentiable, then it should be continuous at that point. This implies f of x is continuous at x equal to c. Next is corollary. So in this corollary, it is same. It is not only for one function. It is true that every differential function is continuous. Okay, it is not only one function. This is true for any function. If it is differentiable, then it is continuous. But remember students, converse is not true. which means if it is continuous, then it should not be true that it is a differentiable. Once again I am repeating, if the function is continuous at one point, or it may be all the point, but we cannot say that it is a differentiable at that point. It is very difficult. It may be or it may not be. So converse is not true. So let me prove this one converse using taking one example. Let me consider the function f of x is equal to mod x. So in continuity topic, you prove that mod x is continuous for all the numbers. Therefore, it is continuous at 0 also. So now mod x is 0 point, at 0 point it is a continuous, but it is not differentiable at 0 point. So this function is the example for this corollary, that converse. If the function is continuous, then it is not differentiable. For that, this is the function example, mod x. Okay, let me prove this one. In continuity concept, it is proved that mod x is continuous for all real numbers. Now I am verifying for differentiability. Now as you studied differentiability, we check it by left hand limit, left hand derivative and right hand derivative. So first let me operate right hand derivative of the function. Limit as h tends to 0 plus. Now c point is 0 point here. F of 0 plus h minus f of 0. So here it is actually c plus h. Now c point is 0 point. So therefore here it is 0 plus h minus f of 0 divided by h. Okay. Now let me substitute what is a f of 0 plus h. F of 0 plus as h tends to 0 plus means it become positive h. Okay, because h is approaching more than 0 to 0, that means it is h only. And f of 0 means in this x mod x you put x equal to 0, it become f of 0 and denominator h as it is. So therefore here h get cancelled, then you will get value f of 0 is 0, therefore you will get value 1. Similarly, left hand derivative, it is operated like this. Limit as h tends to 0 minus f of 0 h minus f of 0 divided by h. Now f of 0 plus h, what it become? Here you can see that h is approaching 0, less than 0 means this function is become minus h and divided by h as it is. So here you understand this substitution. H is approaching 0 point lesser than 0, which means that it become minus h. Okay, and here this cancels and it become minus 1. Here you can see that left hand limit right derivative and right hand derivative both are different, therefore they are not equal. What we can say, mod x is not differentiable at x equal to 0. Thank you, students.